Once again, SpaceX has won the trust of the Space Force with a record-breaking mission leaving ULA in the shadows. This makes the future of ULA and its new Vulcan Centaur rocket all the more uncertain in a space industry now dominated by reusable rockets like SpaceX's Falcon 9. But the challenges for this struggling company don't stop there. The Vulcan's problems aren't just about reusability. They also stem from issues with its solid fuel boosters supplied by Northrop Grumman. So what's really wrong with the Vulcan? Where is ULA headed next? And how did CEO Tory Bruno respond to all the criticism? Find out everything in today's TechMap episode. This year, SpaceX, not ULA, just helped the US Space Force pull off something truly incredible. Something that could change how fast we get critical satellites into orbit forever. So here's the story. On May 30th, a SpaceX Falcon 9 rocket lifted off, carrying the GPS-3 SV08 satellite, a vital upgrade for the global positioning system that billions of people rely on every single day. But here's the wild part. This satellite was prepped and launched in just 3 months. That's right, only 3 months from storage to orbit. For context, the previous record, also thanks to SpaceX, was 5 months for the GPS-3 SV07 launch. And before that, it usually took the Space Force 2 years to prepare and launch one of these birds. So yeah, we're talking about cutting a 2-year process down to just a quarter of that time. That's huge. This kind of rapid launch capability isn't just a flex, it's a game changer. If something goes wrong in orbit, say a satellite failure or interference, the Space Force can now replace or add a new satellite in record time, keeping GPS online for everyone from smartphone users to military operations worldwide. So how did the Space Force manage to move this fast? It all came down to preparation and flexibility. First, they already had satellites built and waiting in storage. Second, and perhaps most importantly, they had rockets ready to fly thanks to SpaceX's Falcon 9. If the Space Force had still been relying on ULA's Vulcan Centaur rocket, this milestone probably wouldn't have happened at all. The Vulcan program faced repeated certification delays, leaving several satellites just sitting in storage waiting for a ride that never came. Eventually, the Space Force made a smart pivot. They shifted several priority missions, including the GPS-3 launches, to SpaceX's Falcon 9, a rocket that's become synonymous with reliability and rapid turnaround. The GPS-3 SV08 mission marked the 7th successful GPS-3 launch on Falcon 9, continuing SpaceX's streak of flawless national security launches. And the Space Force couldn't hide their excitement. They said, "The ability to once again demonstrate a quick-turn launch of crucial capability helps us understand what it takes to make such missions happen and prepare for similar fast timelines in the future." Translation: we can now launch critical satellites fast when it really matters. And that's the real takeaway. This isn't just about one satellite. It's about proving that the US military can respond rapidly to new space challenges. If something unexpected happens in orbit, they now know exactly how to get a replacement up there fast. While SpaceX keeps winning the military's trust with one flawless launch after another, ULA is falling further behind. And things just went from bad to worse. The US Space Force has officially confirmed that it won't be launching any payloads on ULA's Vulcan rocket until next year. So what happened? Well, ULA had big plans for 2025. The company promised up to 10 Vulcan launches this year, a major ramp-up for its brand-new rocket meant to replace the aging Atlas V. But instead of 10, Vulcan has managed just 1 launch. That flight took place on August 12th, marking only the rocket's 3rd mission ever, and its very first carrying a national security payload after finally getting Space Force certification. ULA says the next launch will happen in December, but ironically, not even on Vulcan. It'll be using an Atlas V, one of the older rockets the company has been trying to retire. So why is Vulcan struggling so much? It all goes back to a problem that surfaced during its second test flight in late 2024. One of Vulcan's strap-on solid rocket boosters, the Northrop Grumman GEM 63XL, suffered a malfunction caused by a defect in its nozzle. Engineers traced it back to a manufacturing issue, and that discovery has triggered a lengthy investigation. Now the Space Systems Command is digging through all past flight data and hardware to verify safety before allowing the next Vulcan missions to proceed. In other words, until they're 100% sure the boosters are safe, the schedule is basically stuck in slow motion. And here's where it gets more concerning. This isn't an isolated case. That same kind of nozzle failure has appeared on other Northrop Grumman projects. Back in 2019, during ground testing of the Omega rocket, a nozzle issue caused a major test failure. And more recently, in June 2025, the new booster obsolescence and life extension, or BOL solid rocket motor, designed for NASA's Space Launch System, suffered another nozzle failure during a static fire test. With so many similar incidents, some engineers are beginning to suspect a deeper systemic problem with Northrop Grumman's nozzle design or manufacturing processes. As one commentator bluntly put it, there's something fundamentally wrong with Northrop Grumman's nozzle engineering design models or manufacturing processes. All of this adds up to a huge headache for ULA. Their brand new rocket, the one meant to lead them into a new era of high-frequency, low-cost launches, is now bottlenecked by supplier issues. And in the competitive world of spaceflight launch, cadence is everything. And unfortunately for ULA, the story doesn't end there. Because Vulcan's slow progress isn't just a technical issue anymore, it's now creating ripple effects across its customers, its reputation, and even public confidence in the company itself. These mounting delays have real consequences. For the military, one of ULA's biggest clients, it means critical satellites are sitting on the ground, waiting for a ride that just isn't ready yet. In fact, together with Amazon's Kuiper project, military payloads make up almost 90% of ULA's current backlog. So when Vulcan slows down, so does everyone depending on it. ULA's official goal sounds impressive, to ramp Vulcan up to 2 launches per month, about 24 per year. On paper, that would put them among the world's most active launch providers. But in reality, that dream feels far away. The company insists it's getting closer to that goal, yet clearly it won't happen this year, and nobody knows when it actually will. And part of the holdup comes down to infrastructure. The new rocket assembly hangar and a second mobile launch platform at Cape Canaveral, both essential to scaling up production and launch rate, have also fallen behind schedule. Here's where things really start to sting. Even if ULA did manage to hit that 2 launches per month goal, it wouldn't even be impressive anymore. 5 years ago, that kind of cadence would have been record-breaking. But today, it's just average. SpaceX hit 25 launches way back in 2020, and in 2025, Falcon 9 alone has flown 151 times. To put that in perspective, that's more than a launch every 3 days. Even the old Soviet Soyuz U rocket set a record of 47 launches in 1979, nearly 4 per month, a record SpaceX broke years ago. In other words, the pace of innovation has left Vulcan looking seriously outdated. But the biggest issue isn't speed. It's philosophy. Vulcan is an expendable rocket. Every booster gets thrown away. Meanwhile, SpaceX reuses Falcon 9 boosters multiple times, and Blue Origin's New Glenn is already proving its own reusable design. That puts Vulcan at a massive disadvantage. As one industry watcher put it, Vulcan is definitely 5th behind SpaceX's 3 rockets and New Glenn. Right now, ULA's only unique value seems to be offering a trusted but very expensive option for the US military. And as soon as companies other than SpaceX offer a reliable, reusable alternative, that safety net could disappear overnight. There's also growing concern about the long-term future of solid fuel boosters, like Vulcan's Northrop Grumman GEM 63XLs. Some analysts believe these types of engines are on track to being phased out of civilian rocketry altogether. Solid motors were great in the throwaway era, but in the age of reusable rockets, that philosophy just doesn't fit anymore. As reusability becomes the norm, the focus shifts from cheap to build and discard to robust enough to fly again and again. And that's a shift ULA hasn't adapted to. What do you think? Will Vulcan eventually find its place in the modern commercial space race? Or is it already too late for ULA to catch up? On social media, there's a lot of skepticism about ULA's future and the Vulcan rocket. Many are questioning whether the company can survive in an era dominated by reusable rockets, with some even speculating that ULA might be sold or worse, shut down entirely. One scenario floating around is that Blue Origin could swoop in and buy ULA on the cheap, taking over military contracts and eventually shifting them to their own rockets. On the other hand, some argue that with New Glenn already up and running, ULA might not bring much value to Blue Origin at all. Other possibilities include internal buyout. The most optimistic scenario is one of ULA's current partners, Boeing or Lockheed, deciding to fully acquire the company. Another candidate often mentioned is L3Harris, which already manufactures many of ULA's engines, including the one used on the Centaur upper stage. Finally, there's the post-contract shutdown theory. Once Boeing and Lockheed complete their current orders, they might close ULA entirely unable to compete with the next generation of lower-cost rockets, like New Glenn Neutron Nova and Starship. Now, with all that pressure building, the missed goals, customer frustration, and SpaceX pulling further ahead, you might think ULA's leadership would be staying quiet. But that's not quite what happened. Facing growing criticism, ULA's CEO Tory Bruno decided to push back, and he did it in classic ULA fashion by celebrating precision over speed. On November 25th, Bruno took to social media to highlight one of ULA's recent wins, the flawless Atlas V Viasat-3 F2 mission. He called it a bullseye launch, and honestly, it's hard to argue with that. The mission, which took place on November 13th, marked the 105th successful Atlas V launch, and it wasn't just another routine flight. The rocket delivered the massive Viasat-3 F2 satellite into orbit with pinpoint accuracy, so accurate that the satellite barely needed to use its own fuel to reach its final position. That's no small feat. In an industry where every drop of propellant counts, that kind of precision means the satellite can last longer and perform better. Now let's start with the first bottleneck, the technical hurdles hindering Dream Chaser from obtaining NASA certification. In fact, NASA doesn't hand out certifications easily. It's a meticulous multi-phase process designed to guarantee design integrity, safety, and mission reliability. Here's how it typically unfolds. First, preliminary design review. Confirms the initial design meets requirements. Second, critical design review validates the final design before manufacturing. Third, system integration and testing includes component-level tests, environmental tests, and integrated system tests. Fourth, flight readiness review ensures all tests are complete and the spacecraft is ready for launch. Lastly, post-flight evaluation assesses performance after initial missions to refine certification for future flights. According to updates from both NASA and Sierra Space, Dream Chaser is currently at the culmination of the system integration and testing phase. However, it's still awaiting full NASA certification for two key systems, software and propulsion. This is very important for launch clearance. At the time of editing, the Dream Chaser team is conducting component-level software tests. These are foundational checks that isolate and validate each subsystem, making sure every piece performs reliably and matches design specifications before everything is integrated into the full spacecraft. Once component testing wraps up, the program will move on to integrated system testing, which evaluates how all the hardware and software work together as a single cohesive spacecraft. One of the next big milestones for software certification is called Day in the Life testing, scheduled after December. This simulates a complete mission scenario from pre-launch to landing to make sure the integrated systems, hardware and software, can handle real operational conditions. To bridge the gap between component testing and full integration, Sierra Space performed tow tests in mid-November. This test involves the fully assembled spacecraft being towed along a runway, primarily to verify its navigation software under realistic conditions. At the same time, they completed an environmental test called EMI-EMC. This ensures all electrical systems work harmoniously without interfering with one another, a critical step that supports overall software reliability and certification. In short, software certification is now advancing through component-level and environmental testing, but will need to be completed with system integration testing and finally NASA approval. Full certification will likely be completed after December 2025, possibly as early as 2026. Now, when it comes to propulsion, Sierra Space has already put Dream Chaser's engines through some serious trials. At their Peway facility, the team has completed hundreds of rocket engine firings, all part of the classic component-level testing phase. These tests focus on individual propulsion components to confirm their reliability, performance, and safety before they're integrated into the full spacecraft. But the real challenge lies in what comes next: the major integration tests. There are two big ones still ahead: the acoustic test and the hot fire test. The final round of acoustic testing is currently scheduled for December 2025. This test doesn't directly measure engine performance, but it's crucial. It evaluates how the propulsion system and surrounding components handle intense vibration and sound pressure similar to what they'll experience during an actual rocket launch. Passing this stage ensures the system can endure the extreme noise and structural stress of liftoff. This test is an important prerequisite to upcoming hot fire tests planned for after December 2025 in Colorado. This is the moment of truth, a full-scale firing of the integrated propulsion system to verify performance stability and safety under flight-like conditions. Successful completion of this test is essential before NASA can give the final launch clearance. So where does that leave us right now? As of November 2025, some of the major integration and environmental tests like EMI-EMC and the upcoming acoustic test have either been completed or are actively underway. The next major milestones on the horizon are the Day in the Life test, which will integrate both software and hardware in a full mission simulation, and the hot fire test for the propulsion system. Both are critical for final certification towards the first launch in the fourth quarter of 2026. Although Dream Chaser's progress so far is pretty impressive, there's still one major roadblock standing in the way: propulsion certification. Now, to be fair, both software and propulsion are still moving through NASA's certification process. But if we're being honest, propulsion is the bigger bottleneck here. The engines simply haven't gone through as many of the major validation steps as the software has. For example, Dream Chaser's software systems have already completed key tests like EMI-EMC and tow testing, both critical milestones that prove reliability and integration readiness. The propulsion system, on the other hand, is still earlier in its certification journey. So far, Sierra Space has conducted smaller-scale tests such as rocket motor firings at its Poway facility, but not yet the final major environmental test, acoustic test, not to mention the full-scale hot fire test, which is the true benchmark for engine readiness. And this isn't the first time propulsion challenges have slowed things down. Dream Chaser's launch timeline has already slipped several times from early targets like 2021 and 2023, largely due to ongoing engine-related hurdles. These have included design refinements, integration challenges, and the kind of technical troubleshooting that's common in complex spacecraft development. Dream Chaser's propulsion system uses a hybrid propulsion design that combines hydrogen peroxide as a monopropellant with kerosene as a secondary propellant. This setup is a major departure from traditional spacecraft engines that rely on hydrazine, a highly toxic chemical. By contrast, hydrogen peroxide and kerosene are cleaner, safer, and easier to handle, giving Dream Chaser key environmental and operational advantages. But innovation always comes with extra scrutiny. Because this hybrid propulsion system is relatively novel, Sierra Space must go through a far more extensive testing and validation campaign, essentially building the system's certification record from the ground up. That means not just static fire tests, but also throttle and restart capability, evaluations, integration tests with the spacecraft's other subsystems, and demonstrations of reliable performance across every phase of the mission, from launch to orbital maneuvering to re-entry and landing. And since this system is unique to Dream Chaser, NASA's certification process must verify in great detail that it meets all safety, reliability, and operational standards required for missions to and from the International Space Station. The result, a longer and more complex certification timeline than what's seen with more conventional propulsion systems. It's the price of innovation, but also what makes Dream Chaser stand out as one of the most forward-looking spacecraft in development today. Now, beyond the technical challenges, there's another big factor that could slow down Dream Chaser's path to orbit, and it comes from the outside its launch provider, ULA. ULA has been facing increasing pressure in today's competitive launch market, which is now dominated by reusable, lower-cost and higher-performance rockets. To stay relevant, ULA has been developing its next-generation launch vehicle, the Vulcan Centaur, a modern rocket designed to offer competitive pricing and flexibility for both commercial and government customers. But here's the catch. This transition from traditional rocket tech to modern systems has been slower than expected. The result? A growing launch backlog. Meanwhile, competitors like SpaceX have been rapidly expanding their lead with frequent reusable Falcon 9 launches, tightening ULA's share of the market. And this has had real consequences for smaller customers like Sierra Space. Back in June 2024, Dream Chaser was originally scheduled to fly on Vulcan Centaur's second mission. But due to scheduling issues and ULA's need to prioritize certification flights for U.S. military contracts, Sierra Space's payload was bumped from the manifest. In its place, an inert test payload was flown instead. The reasoning was simple. ULA urgently needed to complete Vulcan's certification for defense missions. With Vulcan's schedule filling up fast in the coming years, it's hard not to wonder if history might repeat itself. And that's where an interesting possibility enters the picture: SpaceX with Falcon Heavy extended fairing option. Dream Chaser measures about 9 meters 30 feet long and 5 meters 15 feet wide thanks to its winged lifting body design. Falcon Heavy's extended payload. Fairing offers around 18.6 meters 61 feet in height and an internal diameter of 5.2 meters 17 feet. This upgrade was designed to accommodate larger and more complex payloads, including missions to the Lunar Gateway and Department of Defense satellites that simply wouldn't fit in a regular fairing. Interestingly, the U.S. Department of Defense helped fund the fairing's development under the NSSL Phase 2 contracts, which shows just how strategically important it is. The only trade-off: this extended fairing isn't built for reusability, It's too large and heavy to recover efficiently. But for unique payloads like Dream Chaser, that's a small price to pay. On November 24th, the quiet hum of NASA's press office broke into a flurry of headlines. The agency had just redrawn its pact with Boeing, an adjustment to the long-troubled Starliner program that once promised a new era of American spaceflight. The revision was stark. 6 missions had been whittled down to 4. The remaining 2 still possible, though now draped in uncertainty, as promises whispered in a storm. The first of those missions, Starliner 1, will not carry astronauts but cargo. Its launch date no earlier than April 2026. Only after that maiden cargo flight will Boeing attempt the most daring Step 3 crewed flights, one at a time each, a test not only of machinery, but of trust. Behind the technical briefings and cautious optimism lies NASA's true mission to certify Starliner as a safe, reliable spacecraft for human spaceflight. Yet the agency's reassurances have not erased the tremors of doubt. For many, memories of last summer's ill-fated crewed test flight remain too vivid to forget those long hours when 2 astronauts found themselves at the mercy of a spacecraft that refused to behave. It's a sobering reality both of Starliner's earlier uncrewed test flights had suffered from thruster malfunctions, and still NASA gave the green light for a crewed mission. What followed was a replay of every engineer's nightmare. The propulsion system, the very heart of the craft, again faltered. 2 years of painstaking fixes, simulations, and hope evaporated in a haze of technical confusion. The root cause of the failure, elusive as ever. The fix, incomplete. One might think the story ends there, but the shadows lengthen when politics enters orbit. Officially, space is meant to be above such things, a political pure, a realm of exploration untouched by earthly disputes. Yet when SpaceX's founder Elon Musk revealed he had offered to return the stranded astronauts earlier and claimed the Biden administration declined for political reasons, the line between science and state blurred. NASA and the astronauts themselves denied politics played any role, but the damage to public confidence was done. Still, the astronauts stayed silent, dignified. Commander Butch Wilmore, ever the professional, declined to comment on the political drama out of respect for NASA and the administration. His restraint spoke volumes, a quiet act of loyalty in an age of noise. Behind the scenes, their ordeal was more chilling than most realized. Imagine it 9 months trapped in orbit, waiting, watching, hoping yet unable to speak the full truth. You endure the fear, the uncertainty, and when you finally return home, you thank everyone because that's what astronauts do. It wasn't until nearly a year later that the real story began to surface. In April, an Ars Technica report pulled back the curtain on the harrowing moments aboard Starliner. The reactions were visceral. Commenters called it terrifying, a shit show, even the worst possible failure without deaths. One simply wrote Jesus. Now, as Boeing and NASA prepare to try again, the stakes are painfully clear. This is not merely about contracts or cargo. It is about trust in a national space agency, once seen as the steady hand guiding humanity's reach for the stars. Trust in a company whose name once stood as a monument to American aerospace ingenuity. And yet beneath that trust lies an uncomfortable truth. There is no confidence left in a program that has never truly succeeded. We can't forget what Wilmore and Williams said during their interview with Ars Technica back in April. The unease began quietly, first in their voices, then in their eyes, when they spoke of what they would later call the cold night on board. The crew endured it in silence. Starliner was designed for 4, but this maiden voyage carried only 2, and the absence of extra bodies meant the absence of warmth. By Wilmore's estimate, the cabin dipped to 50 degrees, Fahrenheit perhaps colder. The two astronauts, wrapped in their bulky suits and boots, floated through the capsule like explorers in a frozen cave, each exhaling, fogging the air between them. Yet the chill in the air was nothing compared to the cold that settled in Wilmore's gut. He couldn't shake the worry about Starliner's 28 reaction control system thrusters, the very engines that kept the spacecraft stable and steerable in orbit. He had raised those concerns long before launch, reminding senior Boeing officials that the same thrusters had failed during unmanned tests. His fear was simple, blunt, and chilling. If we lose thrusters, we could end up in a situation where we can't control space. That moment came sooner than anyone wanted. On day 2, as Starliner approached the International Space Station, the mission reached its most delicate phase, docking along the V-bar, the invisible velocity line trailing the orbiting outpost. Every meter mattered. Every pulse of a thruster counted. Then suddenly one didn't. A single thruster failed, forcing Wilmore to take manual control. Moments later, a second went dark. Starliner was now down to a single fault tolerance to maintain 6 degrees of freedom forward, choco backward, up, down, left, right, yaw, pitch, roll. It is just one layer of redundancy separating order from chaos. The loss of 2 thrusters violated the mission's flight rules. At this point, they were supposed to abort, turn around, and head home. But home wasn't a simple choice anymore. As the craft edged closer to the station, a 3rd thruster died, then a 4th. The pattern was alarming. They were all aligned in the same direction, 2 underneath and 1 along the port side. Wilmore had now lost 6 degrees of freedom control. The ship couldn't maneuver forward. The controls felt sluggish, like pushing through syrup in zero gravity. That's when the question loomed, one that could decide everything. Go forward or return. Turning back meant relying on the same faulty thrusters to re-enter Earth's atmosphere. But pressing forward risked colliding with the station. Every option was dangerous. Every second stretched thin. "We're in a very precarious situation," Wilmore admitted. At one point, he confided a thought no astronaut ever wants to voice. "I don't know if we'll be able to get back to Earth. I think we probably won't." Ahead of them, the ISS shimmered against the void, so close, so impossibly far. The astronauts agreed their best hope of survival was to dock, seek shelter, and let the ground teams figure out what had gone wrong. In Houston, the room fell silent, except for the hum of consoles. Flight Director Ed Van Cees made a fateful decision: waive the flight rules. It was a call born of experience, courage, and perhaps desperation. Mission Control became the 3rd crew member that day. To save the mission, engineers needed to restart the failed thrusters. But for that, Wilmore would have to take his hands off the controls, relinquish command of a drifting spacecraft in orbit just hundreds of meters from the ISS. Hands off, he radioed, his voice steady but tight. Houston sent the command. The flight computer rebooted. 2 thrusters sputtered back to life. Starliner clawed its way back to a single fault state. Then, as if to mock their relief, a 5th thruster failed. The team on the ground tried again, one more restart, one more act of faith. Miraculously, all but 1 engine returned. It was enough. With cautious optimism, Wilmore handed control back to the automated system. Starliner bruised, but breathing performed its final maneuvers and almost disbelievingly docked. Cheers erupted in Houston. On board, Williams allowed herself a small smile of joy. But beneath that moment of triumph ran a quiet dread this spacecraft had barely made it to port. Wilmore knew it too. As he later put it, "I didn't think we could do it. I was hopeful, but it was going to be really hard to get to the point where we could say, yeah, we can come back." That night, as Earth rolled beneath them, the 2 astronauts floated in silence, still wrapped in their suits. The cold had returned, but now it wasn't just the temperature. It was the realization of how close they had come to being stranded among the stars. In the days that followed, the truth began to crystallize, not in the number of thrusters that failed, but in what those failures nearly cost. At first, the headlines were clinical. 4 of 28 thrusters lost. A statistic, a fraction, a data point. But buried in the telemetry logs and first-hand accounts was a far more terrifying reality. Starliner had come within reach of total loss of control, 6 degrees of freedom slipping away one after another, like a pilot's nightmare unfolding in slow motion. Engineers later admitted that the spacecraft's roll and lateral axes were at the brink of collapse. They lost control of 6 axes, one analyst summarized bluntly, calling the situation horrifying. Behind the restrained technical jargon, one conclusion echoed through engineering circles and comment threads alike. Boeing had really profoundly messed up. But Boeing wasn't alone in the crossfire. NASA too found itself under intense scrutiny, not for what happened in orbit, but for what happened afterward. The agency's legendary commitment to openness seemed to falter. Days turned into weeks before the public learned the full extent of the crisis. Questions multiplied. Why did it take so long for NASA to reveal that the astronauts would not return on Starliner? Why were the most severe details buried beneath a tide of vague reassurances and silence? The opacity sparked suspicion. It felt like a cover-up, one industry observer said, like they were trying to sell confidence they didn't actually have. Until now, in the hallways of Houston and the hangars of Cape Canaveral, an unspoken question lingers heavy as vacuum. Who would dare climb aboard Starliner now? According to Eric Berger, Ars Technica's senior space reporter, NASA astronaut Luke Delaney was also in line to train for the Starliner 1 mission at one point, but has been reassigned to the SpaceX Crew 13 mission. There are some astronauts who have trained to fly on Starliner and were reassigned to fly on SpaceX's Dragon spacecraft, who could conceivably be assigned to the Starliner 2 flight, assuming all goes well with this next cargo mission. On November 27th, Russia launched a Soyuz spacecraft from a place called Site 31, located at the Baikonur Cosmodrome in Kazakhstan, to send astronauts to the ISS as usual. The launch worked, and the crew got to the ISS safely. But after the launch, something went wrong. A huge 20-ton platform. Think of it like a big support structure wasn't secured properly and fell into a pit called the Flame Trench by the rocket's thrust. There is significant damage to the pad. This is clearly a strategic loss for Russia. Site 31 at Baikonur is the only Russian pad currently configured to launch the Soyuz rocket, and 2 spacecraft critical to the space station, the cargo-only Progress vehicle, and the Soyuz crew capsule. The temporary loss of launch capabilities from Pad 31 has raised concerns about the lack of Progress launches. According to an internal schedule, there are 2 Progress vehicles due to launch between now and July 2027, followed by the next crewed Soyuz mission next summer. And here's why that's a huge deal. Site 31 is currently the only Russian pad configured to launch the Soyuz rocket, the lifeline, for both the Progress cargo ships and the Soyuz crew capsules that keep the ISS running. With that pad now out of commission, Russia faces a serious bottleneck. According to internal schedules, 2 Progress missions were supposed to launch before July 2027, with another crewed Soyuz flight planned for next summer. But now everything's on hold. This is more than just a scheduling headache. The Progress spacecraft is the unsung hero of the ISS. It doesn't just haul up food, water, and gear, it's also responsible for reboosting the station's orbit. Over time, the ISS gradually loses altitude because of atmospheric drag, and Progress is what pushes it back up. Yes, American vehicles like Cygnus and Dragon can help with reboost, but here's the kicker. The real concern isn't just altitude, it's attitude control. The ISS stays stable in space thanks to a delicate dance between US gyroscopes and Russian thrusters. But those thrusters rely on fuel that's only delivered by progress. And if there's no progress, the Russian segment runs out of propellant. While it's theoretically possible for US supply ships to bring fuel, there's currently no practical way to transfer it into the Russian propulsion system. So here's where things get really interesting. The temporary loss of Pad 31 doesn't just slow down Russia's space operations, it actually puts more pressure on SpaceX to step in. According to a source familiar with NASA-Russia relations, SpaceX might be called upon to back up Russia during this downtime. Now, SpaceX has already proven that it can help with one of the ISS's biggest needs, reboosting its orbit. The company successfully demonstrated this a while ago using a modified cargo Dragon with a special trunk section, and the test worked flawlessly. It's a neat, clean solution that doesn't require any complex engineering workarounds like welding extra communication gear onto the station just to make things talk to each other. But that's not the only idea floating around. Some in the space community are suggesting we could bring back something like the ESA's Autonomous Transfer Vehicle, or ATV, if you remember those ATVs used to haul tons, literally, of supplies to the ISS. In fact, each one could carry 3 times more cargo than a Progress spacecraft, and they also had the ability to boost the station's orbit. So in theory, an upgraded or next-gen ATV could fill in the gap left by Progress. That said, reboosting isn't the real nightmare here, attitude control is. Cargo Dragon and Cygnus might be great at delivering supplies and pushing the station higher, but they can't refuel the Russian thrusters that help desaturate the station's gyroscopes. However, a proposed technical solution is that if a cargo ship can push the ISS upward by firing its main engines straight through the station's center of mass, COM, the torque needed to desaturate the gyroscopes could be provided by firing smaller thrusters off to the side instead. Cargo ships like Dragon have clusters of these thrusters placed away from the COM line, so operators just adjust how long each one fires by changing pulse timing to create the exact twist needed to reset the gyroscopes. Of course, people have also floated the idea of launching Progress on a completely different rocket, maybe a Falcon 9. Sounds cool, right? Unfortunately, that's not realistic. Progress depends on a specific kind of hot fire separation during launch, which Falcon is built for. Add in the costs, the logistics of getting a Russian spacecraft ready for launch from US soil, and yeah, not happening anytime soon. Then there's the wildcard question: could Starship eventually boost the ISS? In theory, yes, Starship's engines are more than powerful enough. But in practice, probably not anytime soon. Even one of those engines running at low power could shake the station like a tin can. Plus, Starship hasn't even performed a docking or approach test with the ISS yet, so the risks are off the charts. But what do you think? Should SpaceX become the go-to backup for ISS stability? Or should NASA and its partners build a new dedicated vehicle for the job? Drop your thoughts down in the comments. I'm really curious where you all stand on this one. So here's the bigger picture. This whole incident doesn't just damage Russia's Soyuz launch pad. It also shines a bright light on something that's been quietly building for years: SpaceX's growing monopoly on crew transportation to the ISS. Right now, SpaceX's Crew Dragon is the only NASA-certified vehicle capable of taking astronauts to the ISS. Boeing's Starliner is still in test mode. It needs to complete one more uncrewed mission before NASA signs off for human flights. That means for the foreseeable future, Dragon is the only ticket to orbit. But that's not all. The dependency runs even deeper. The Cygnus cargo vehicle, which delivers supplies to the ISS, now also relies on SpaceX's Falcon 9 rocket to reach orbit. Yep, both Dragon and Cygnus are flying on Falcon 9s. At this point, Falcon 9 is the only operational rocket launching both crew and cargo to the station. As Ars Technica's space editor Eric Berger summed it up perfectly, it's crazy to think about it, But if there's any emergency on the ISS at this point, it means all the responsibility falls on SpaceX. Crew Dragon, Goods Dragon with Cygnus, Reboosts Dragon with Cygnus, Quest Explanation Dragon. Basically, SpaceX is holding up the entire operation. Now, there are some big advantages to that. SpaceX has been flying astronauts to the ISS since 2020, and they've proven themselves time and again. If there's an emergency, say, an astronaut gets sick, or there's a critical system failure, SpaceX can scramble a rescue mission faster than anyone else. We saw that last year when a Crew Dragon was repurposed to bring home Boeing's stranded Starliner astronauts after a technical issue. So reliability check, experience check, speed definitely check. And because Dragon can do pretty much everything, carry people, haul supplies, and even perform reboosts to nudge the ISS into a higher orbit. NASA's got an all-in-one solution. Normally, Russia's Soyuz and Progress handle those jobs, but with their pad out of commission, SpaceX is doing it all. It's like having one incredibly reliable friend who handles all your chores, cooking, driving, cleaning while everyone else is out sick. Another plus cost. SpaceX's reusable technology means they can fly cheaper than traditional programs. NASA doesn't have to pay multiple providers like Boeing or international partners just to keep missions running. That money can go toward new exploration programs, moon missions, Mars projects, you name it. And with over 20 successful ISS missions under its belt, Dragon is battle-tested. Its launch escape system can pull astronauts to safety if something goes wrong during liftoff, and those ocean landings with parachutes, smooth and proven. It's no wonder NASA trusts Dragon more than ever. But here's where it gets complicated. This level of dependency can be a double-edged sword. SpaceX is already juggling an enormous workload, launching Starlink satellites by the hundreds, testing Starship, and now potentially shouldering all ISS logistics. That's a lot, even for them. If the company gets stretched too thin, it might mean higher prices delays or fewer rockets available for other missions. And with Russia's involvement in the ISS possibly shrinking due to economic strain and the war in Ukraine, that pressure on SpaceX is only going to grow. Meanwhile, the ISS itself needs regular reboosts to stay in orbit. Traditionally, Russia's Progress ships handled that. SpaceX can do it too. They've successfully boosted the ISS before using Cargo Dragon, but it burns more fuel and adds cost. This situation is like a team project where one person, Russia, can't do their part, so the other team, SpaceX, has to pick up the slack. It might work out, but it could get stressful and expensive. Space fans are watching to see if SpaceX can handle it, or if the ISS plans will change. Does that make sense? Let me know. This incident also raises serious questions about the state of Russian technology. The Soyuz launch pad failure isn't just a random accident, it's a glaring sign of flaws in operational procedures and quality control. The 20-ton service platform is essential for preparing the engines before launch. Yet it was left unsecured and destroyed, a mistake that points to serious gaps in final inspections and safety protocols. Some people couldn't resist sarcastically commenting that QA based on vodka is working. To put it in perspective, the magnitude of this error has been compared tongue-in-cheek to everyday forgetfulness, like leaving your car out of park and walking away. But the implications go beyond just one launch. Public discussion suggests that these quality issues may be systemic. Experts are asking whether this decline in quality spans all Russian aerospace projects, including strategic missile programs. One pointed comment notes that a recent failed test of the Sarmat ICBM destroyed its test launch facility. This isn't an isolated incident. Key Russian launch sites have been accidentally destroyed before suggesting deeper operational and quality problems. Unveiled in Shanghai in late April, Qingzhou's design was inspired by Dragon, along with Europe's ATV and Japan's HTV, to create a compact 2-ton cargo hauler. Qingzhou, or Lightship in Chinese, is China's next-generation cargo spacecraft, built for resupplying the Tiangong space station and future orbital missions. Unlike Dragon's 2-module setup, Qingzhou goes all in with a single capsule design, packing 27 cubic meters of cargo and a 2-ton capacity. In contrast, SpaceX Cargo Dragon uses a traditional 2-module design, a pressurized capsule, 9.3 m3, and a separate unpressurized trunk, 37 m3. The spacecraft supports a launch payload capacity of 6,000 kg 13-28 lbs to low Earth orbit, such as the ISS, with a return capacity of 3,000 kg 6,114 lbs. Qingzhou's compact design isn't just sleek, it's flexible. Qingzhou can ride on multiple rocket types, not just a dedicated launcher like Falcon 9, giving China more options for orbital logistics. Inside it features a 4-tier shelving system with 40 compartments ready to handle all kinds of cargo. But here's where Qingzhou really stands out. It's essentially a high-tech warehouse in space. Using image recognition algorithms and high-def cameras, it tracks inventory in real time, no manual logging required. Astronauts can even search by voice, instantly accessing the cargo database for faster, smarter mission operations. Dragon great at hauling cargo, but it doesn't automatically track inventory like this. Qingzhou is stepping into orbit not just as a cargo carrier, but as a smart astronaut-centered logistics platform. One standout feature: Qingzhou's state-of-the-art cold chain system, designed to transport up to 300 liters of temperature-sensitive cargo using fully modular reefer containers. Each container holds 60 liters and operates independently, meaning you can mix and match temperature zones. Need fresh vegetables in one compartment and frozen medical samples in another? No problem. Dragon can handle cold storage too, but it doesn't offer this level of modular flexibility. Taking a page from SpaceX, Qingzhou is built to be reusable, and that's where the single capsule design really shines. Think of Dragon like a 2-part toy, a front backpack, the capsule, and a big back wagon, the trunk that gets discarded after each flight. Qingzhou 1, simple capsule, like a single lunchbox with everything inside. With Dragon separating and discarding the trunk takes time, tools, and safety checks. Qingzhou skips all that. One piece means quicker turnaround, easier inspections, and faster reloads after landing, like washing one lunchbox instead of 2. Its compact, simple shape also fits a variety of rockets without the custom adapters Dragon needs for its trunk. That flexibility allows fast launches on whatever rocket is ready, making back-to-back reuse missions more efficient. Fewer parts mean shorter prep time before liftoff, weeks faster than Dragon, perfect for keeping supply lines to the station flowing smoothly. If Qingzhou goes into operation, it could spark a quiet revolution in China's space program, while also building the skills and infrastructure needed for the lunar race. Its frequent, cost-effective resupply missions to Tiangong free up budget and resources for moon-bound projects like Chang'e 7, the kind of quick, efficient wins China pulled off with U-2 on the moon's far side in 2019, all while Artemis continues to face delays. Operating a reusable intelligent cargo spacecraft like Qingzhou isn't just about sending supplies, it's a training ground for docking, re-entry, and autonomous operations. These are the exact technologies China will need for lunar orbiters, landers, and eventually building the International Lunar Research Station (ILRS) by the 2030s. Qingzhou can auto-dock with Tiangong using robotic systems, and the same tech could let Chang'e 7's lander and rover dock at the moon's south pole to hunt for water ice in craters, potentially beating NASA's delayed Artemis 3. On its way back, Qingzhou re-enters Earth safely, like Chang'e 5X brought back moon rocks in 2020, cutting costs for future moon cargo missions and stocking robotic bases before humans even arrive. That said, While Qingzhou gives China strategic advantages, it still lags behind the US in proven technology and large-volume transport capacity. Qingzhou has just been unveiled and is slated for launch in September 2025. That means it still has plenty of time for testing before earning full certification. Meanwhile, Dragon has been flying for over a decade with an almost flawless record. This operational experience gives SpaceX a huge edge. Decades of docking re-entry and orbital operations have set the stage for the next big leap, Starship. Here's the reality. There's a huge gap between China's current capabilities, small spacecraft, and rockets, and the US's long-term potential, which includes sending full-sized manned spacecraft to the moon. The payload difference isn't just big, it's staggering. It's not even in the same ballpark. At best, it's barely in the same sport. And that gap comes down to one undeniable advantage: Starship. Starship is designed to deliver 100 metric tons of cargo to the lunar surface, and it can also serve as a manned lander and habitation module. As Elon Musk often says, there is no substitute for mass to orbit. The first Starship HLS could deliver more material to the moon than all other lunar landings combined in history. So yes, China is making impressive strides. But at the end of the day, they don't have SpaceX. Without Elon Musk pushing the envelope, the current space race could look very different. Yet as long as Elon and SpaceX keep delivering, the US-led lunar programs are poised to maintain clear superiority well into the 21st century. At the end of the day, space isn't a sprint, it's a marathon. And in marathons, proven systems win. Dragon has decades of experience, countless missions and lessons learned the hard way. That's why SpaceX can confidently take the next leap with Starship, while newcomers like Qingzhou still have a long testing road ahead. So next time you watch a new spacecraft debut, remember innovation is exciting, but experience carries the finish line. Proven systems don't just survive, they dominate. In addition to Qingzhou, China is developing a reusable shuttle called Haolong, designed to ferry cargo to and from its Tiangong space station. Haolong's development comes as China plans to significantly expand its space station in the coming years. This shuttle could offer a cost-effective and versatile way to maintain operations in orbit. Much like NASA's retired space shuttle Haolong is a winged spacecraft, it launches atop a rocket and lands on a runway like an airplane. It features a blunt-nosed fuselage and large swept-back delta wings. This design blends the characteristics of both spacecraft and aircraft, enabling it to reach orbit and return safely to Earth. Interestingly, Haolong weighs less than half of China's Tianzhou cargo spacecraft, which is currently used for resupplying Tiangong, making it a lighter and potentially more efficient option for future missions. Now, let's take into the most intriguing part, comparing Haolong to Dragon. China's Haolong spaceplane and SpaceX's Dragon represent distinct approaches to reusable cargo spacecraft with different strengths and capabilities. Haolong is a winged reusable cargo spaceplane about 10 meters long with an 8-meter wingspan and a mass near 7,000 kilograms. It is designed for runway horizontal landing and aircraft-like reuse, featuring a rear docking port and an accessible cargo bay. Haolong's payload capacity to the Tiangong space station is around 1,800 to 2,000 kg, and it will launch on the commercial Chinese Zhuke 3 rocket. As of 2025, Haolong is in the engineering development and testing phase. At this point, I can't help but get a sense of déjà vu with Sierra Space's Dream Chaser. Both are ambitious winged cargo shuttles, but if history is any guide, Haolong might still be several years away from becoming operational. In contrast, SpaceX's Dragon is a capsule-style reusable spacecraft, approximately 8.1 meters in length, with no wings weighing around 12,000 Telskor in its crewed configuration. It supports vertical propulsive landings on Earth and is capable of multiple reuses per capsule. The Dragon can carry much more of combined pressurized and unpressurized cargo, and is versatile enough for both cargo and crew missions to the International Space Station, as well as private missions. Dragon launches atop SpaceX's Falcon 9 rockets and boasts over 35 successful cargo missions completed to date with ongoing crew flights. While Haolong's winged design offers a unique cargo delivery and runway landing method potentially lowering turnaround times and maintenance complexity, its lower payload capacity and current unproven flight status mean Dragon still leads in operational maturity, mission versatility, and cargo volume. Dragon's extensive flight heritage, larger payload, and dual cargo and crew roles affirm its status as a battle-tested workhorse, while Haolong targets a niche in China's Tiangong cargo resupply with long-term ambitions for routine and cost-effective spaceplane operations. Shifting from uncrewed spacecraft to crewed missions, China is set to launch its next-generation crewed spaceship, Mengzhou 1, in 2026, according to the China Manned Space Agency. Mengzhou 1 is a major upgrade of the Shenzhou crewed spacecraft, featuring a modular design with a return capsule and a service capsule. Its primary mission will be to transport astronauts between Earth and the Tiangong space station. The maiden flight of Mengzhou 1 is planned atop the Long March 10A carrier rocket launching from the Wenchang Space Launch Site in southern Hainan Province. Once in orbit, it will dock with the radial port of the space station's core module, marking another step forward in China's human spaceflight program.